Welcome to the Automotive Diagnostic Podcast. We're going to explore ways to sharpen our diagnostic skills, find learning resources, and hear from experts in the automotive field. What's up, automotive friends? How is everybody doing today? This is the Automotive Diagnostic Podcast. My name is Sean Tipping. I will be your host today. Thank you so much for tuning in. Let's jump right into it. Today, we are going to be talking about engine mechanical testing. So this is a mechanical problem with an engine, a piston with a hole in it, a bent rod, a broken valve spring, worn camshaft lobe, something like that, a mechanical failure of the engine, but testing using a scope. All right. There's a lot of material out there on scope tests for engine mechanical problems. Obviously, we can use scopes for a lot of electrical things, and I love pulling my scope out for just about any reason that I can. But one of the areas where I think they really shine, and in the general population of technicians, they're not used in this manner as much, although it is definitely growing, thanks to some people that I'm going to mention that have shared their knowledge in this area. And I should probably say right up front, I'm not an all-knowing master or guru of these techniques, but I've used a lot of them, and they've been really helpful. So again, to sum this up, is we're going to be talking about how do we test the mechanical operation of an engine using a scope. And this would be in replacement of, or sometimes in conjunction with, our traditional testing methods for analyzing the mechanical state of the engine. And I'm actually going to go through those first, the techniques and the tools that most of us were taught to use when we went through tech school or we were trained about analyzing mechanical state of an engine, and we'll jump into the three main ones here. So first one, very simple test, is our vacuum gauge, and I still use a vacuum gauge quite a bit. It's a very useful tool for a number of reasons, but traditionally speaking, vacuum level and stability is a great indicator of how an engine is running. Now we can infer a lot from the level of vacuum, the stability of vacuum, and there's a number of different ways you can use a vacuum gauge to determine how an engine's running. You can even use it during, a cranking vacuum test to see if there's a vacuum leak in the engine. Lots of different uses for a vacuum gauge, and it's easy. Okay, find a vacuum source, preferably centralized on the backside of the throttle body, and take a look to see what your gauge is reading. Now, the one time where this becomes less effective in newer engines is we're seeing a lot of engines that don't develop as much vacuum as engines of the past, and this has to do with direct injection and the way that the throttle bodies are operating. Now, some of the time they might develop vacuums, but we're seeing a lot of engines. I mean, take a look under the hood on a lot of these newer vehicles. They've put vacuum pumps on a lot of these vehicles to create enough vacuum for the brake booster, and that's because we're not always developing sufficient vacuum in the intake manifold, again because of direct injection, or even in the case of a BMW, they have their Valvetronic, where they're controlling airflow with valve movement. Anyways, a little off subject there. Point of the matter is, a vacuum gauge has always been a very reliable tool to give us insight into the health of a running or even cranking engine. Hook it up to the intake manifold, read the gauge. I'm not going to go through, what all the gauge readings mean, but one of the things about the vacuum gauge that really is just, you've got this problem, is if you hook it up to a running engine and you see that needle rapidly fluctuating or bouncing, guess what? You got a mechanical problem. You've got a broken valve spring, or something wrong with a valve, or a hole in the piston, something along those lines, right? You see a bouncing vacuum gauge, that's it. Find your mechanical problem. So we've used that. It's a great tool. I'm going to show you how we use some of the scope tools in a similar manner. And kind of the reason I'm going through these older tools is sort of compare the newer, some of these techniques have been around for a while, but newer styles of testing using the scope, how do they compare to the old ones that most of us are used to using? Next one, tried and true, good old compression gauge. All right, and most of us were taught how to measure compression of a cylinder with a compression gauge. This is going to thread in place of where the spark plug is. We're either going to crank or run the engine, and we're going to look at that needle to see how much compression is this cylinder making. And this is probably the one tool where I don't use an old-fashioned compression gauge very often anymore, and I will describe why in a couple of case studies where a compression gauge can lead you astray. Not that it's totally useless, and not that it's not simple to use, but I think there's better ways that we can analyze the engine besides a mechanical compression gauge. Third test that we use for mechanical analysis of an engine is our cylinder leak down test, and this is basically a tool that is going to allow you to put compressed air into a cylinder and analyze not only how much air it's leaking in a percentage, but you can also tell where it's leaking. So we put the air into the cylinder and we watch. There's going to be a gauge on the tool that's going to tell you a percentage of leak down, how much air is escaping the cylinder. Now, what that number should be does vary depending on the manufacturer, but I don't like to see a whole lot over 20 to 30%. If I see that on a vehicle, I'm going to be concerned. Now, I can't say that's true across the board because I actually have the students run through these old school tests. They need to because there's questions about them on the ASE test, and there still is a place for a leak down test. I really do think there is, and I'll explain that. Anyways, I have them run through the cylinder leak down test so they know how to do it. My personal car that I drive is a 2003 Buick Park Avenue with a 3800. It's got 280,000 miles on it. It's a tired old engine, but she just keeps going. And number one cylinder on that engine has a pretty severe leak down. It's upwards of 60 to 70%, but I don't have any misfires, and I really don't have that much oil consumption either. And it's all past the rings. It's just worn out. Is there a noticeable problem that I need to address with my vehicle right now? I don't feel like there is. I drive this thing every day, and it runs solid. Could it be better? Sure. But what I'm trying to say here is that the numbers, take it with a grain of salt. There are some manufacturers that say, hey, if this is over 15%, I've seen numbers as low as that, you've got a problem, you need to address it. So take that with a grain of salt. I usually want to see somewhere under 20 to 30% leakage. And again, that's 20 to 30% of the air that you're putting in is getting leaked out. Now, you're always going to get some past the rings. That's normal. But we can also listen into the intake through the throttle. We can listen through the exhaust and see, do we hear air rushing out of those places, or through the dipstick tube, oil cap, to see if it's going past the rings. So those are the areas that we can leak compression from. We can have it go past the rings or past the piston somehow. We can have it leave through the exhaust valve, through the intake valve. You could also have it escape through the head gasket into the cooling system, so you can look for bubbles there. And I guess even on newer vehicles, you could have a seal from an injector on a direct injected vehicle leak. I haven't personally encountered that, but I'm sure that's definitely possible. So I guess we added one more place where we could lose compression. Anyways, that's our cylinder leak down test. So those are our three traditional tests that we use: a vacuum gauge, a compression gauge, and a cylinder leak down tool. Now, is there anything wrong with these tests and these testing methods, these tools? I don't think so. I think they're all reliable and they can all be used to figure out what problem you have with an engine. If these are the three tools that you have, that you like using, there's nothing wrong with that. And I'm not going to say anything otherwise. The cost of the cylinder leak down test will be a little bit more expensive, but here's the let me tell you how you could do a cylinder leak down test. Take the Schrader valve out of your compression tube, get the cylinder up to TDC, on the compression stroke, thread your adapter in. So this is your adapter for your compression gauge. So this threads into the spark plug tube, and on the other end it has an air fitting. And instead of putting that air fitting to your gauge, which you normally would do for a compression test, you hook up shop air directly to that. Now this is going to be a little bit more pressure than the leak down tester is actually going to put through, and you're not going to see a number, but use your ears, figure out where it's going. If you've done enough of these, you can tell whether it's leaking enough to cause a problem. So what I'm saying there is, I guess you wouldn't have to buy a leak down tester. That's what I did for the first few years of my career, because I didn't have a leak down tester. So that's, a cheap, effective way to do this. A compression gauge set, a nice set's going to cost you a few bucks, but it's not terribly expensive. And a vacuum gauge, you're looking at spending $25. So you can have all this equipment and you can do all the testing techniques that you need to without anything more expensive. But we're talking about scopes today, and I want to give my perspective on why I think scope testing can be more effective, can be time-saving. There are areas where I know it can be time-saving as opposed to these traditional test methods, and it can just be more accurate in our diagnosis. So let's talk about some of the tests that we can do. Again, analyzing engine mechanical problems using a scope. First one, my favorite, this is one of the game changers for me, was a relative compression test. So if you're not familiar with the relative compression test, make yourself familiar. If you take one thing away from this podcast and you're not doing relative compression testing already, you need to be doing it. I'll just tell you that right now. You need to get a scope and get an amp clamp. Heck, you don't even have to get an amp clamp. You could do this with battery voltage. I'll talk about the test in a little bit here. But if you're not doing a relative compression test, ask yourself, why not? Why am I not doing this? This is just such an awesome test. I wish so much that I would have had this test for years and years earlier in my career, because man, is it a time saver. So let's back up a minute here. Let me explain how a relative compression test works for anyone who's unfamiliar. Now, we need to have a scope of some sort. Now, you can do this with a snap-on scope. You can do it with a U-scope. A little tougher to see the detail on it, but it can be done. Or you can do it with my favorite, the Pico. The zoom function is awesome on the Pico scope, so you can really get into the detail here. But what we're doing is we are taking an amp clamp, which just hooks around a cable, and it is going to measure the inductively, non-intrusively, it's going to measure the amperage that the starter is pulling. That's all we're doing. Okay, so we're going to either hook this around the negative cable or the positive cable. As long as it goes to the starter, doesn't matter. You just have to flip the clamp around depending on the direction of current flow. We're going to hook this up to our scope. We are going to disable the engine from starting. In a lot of cases, domestic vehicles, that just means holding the throttle down, wide open throttle, putting it into a clear flood mode. And you don't have that option on all vehicles. So you may have to disable fuel or spark. I would always recommend disabling the injectors if possible. Here's the reason why. Let's say you disable the fuel pump. Okay, you take the fuel pump relay out. There's still going to be some fuel pressure, and it's going to try to start while you're doing this test, and you'll get some inaccurate readings. Even if it doesn't, you're still dumping some fuel in there, which can actually wash the cylinders down if you crank this thing long enough, and it can throw off your readings. So if you disable the injectors somehow, whether that's a fuse or sometimes it's easy to unplug them, I realize that's not always the case, but if you can find the fuse that powers the injectors, heck, that is the way to go. And that way you've got no fuel going in there and no possibility of this thing starting, and we could just rely on our starter amperage for turning over that engine. And that's what we're doing. So with this test, we take our starter amperage, the current that the starter motor is drawing while it is cranking the engine over. Okay, so all of our pistons in the engine are going through their 4-stroke cycle even when the engine's cranking. So we have intake, compression, power, exhaust. What we're really looking at is the compression stroke. And when that starter has to push a piston up on the compression stroke, it's going to push against some resistance, right? If you've turned an engine over by hand ever, which I imagine most of us have, you feel that resistance as you come up on a compression stroke of a cylinder. You're squeezing that air. And the starter encounters this as well. So the starter has to work harder. It actually slows that starter down just a little bit as it comes up on the compression stroke of a particular cylinder. And as that starter slows down, it is going to raise the amperage. So our starter motors in a gas engine, we're not talking hybrid here, but in a gas engine, our starter motors are a brush style DC motor, which means for that style of motor, as the load increases and we slow down that starter motor on a compression stroke, we raise the amperage. Now, once we get to the top dead center there on our compression stroke and we start to go on the power stroke, now that engine speed and the starter speed is actually going to speed up. And as an electric motor speeds up, the current is going to drop. And this all has to do with counter electromotive force inside the circuit. That part of it's not really important, but if you want to understand what you're seeing, it is good to understand how an electric motor works. Anyways, we hook up our amp clamp, we put it to our scope, we disable the engine from starting, we crank it over, and what we see on the scope is each compression stroke represented by current draw of the starter motor. And this is huge because here's what you can do. That starter motor is going to push against every single cylinder in that engine in succession, in the firing order that it normally would as the engine was running. And so you get to see every single cylinder. If that is a 4-cylinder, you see all 4 cylinders. If it's an 8-cylinder, you see all 8 cylinders. Heck, if it's a 12-cylinder, you see all 12. And imagine trying to test the compression of all 8 cylinders mechanically with a gauge like I've done many, many times. You've got to take all the spark plugs out and then put that gauge into each cylinder opening and crank it over each time and record your numbers. When this test takes you maybe 5 minutes to hook up an amp clamp, turn on your scope, disable the engine from starting, sometimes that's a little bit of work, and then crank the thing over. And what you are getting is a quick assessment of the mechanical health of that engine. Okay, so if you got a mechanical problem with a piston, with rings, with a cylinder wall, with a valve spring, with a valve seat, with a camshaft lobe, any of this stuff, it is going to show itself in the cylinder's ability to compress air properly. And maybe I should say this differently, to breathe properly, because to compress air, we've got to be able to take air in. We've got to have a cylinder that seals in order to compress it, and we have to evacuate that air on our exhaust stroke. If any of those things can't happen, well, guess what? The compression's not going to be correct. Now, sometimes it'll be low. Heck, sometimes it'll actually be high, depending on the problem that you have, but again, getting back to the point, this is such a quick test that tells you so much about the mechanical aspect of the engine. It was such a big deal for me when I finally was shown how to do this test, and I was like, holy crap, why have I not been doing this for forever? You should buy a scope for this reason. That is my honest opinion. If you don't have a scope and you're like, man, I don't really want to get into the scope stuff, it just seems too crazy, buy a scope just for this, and it will pay you back. It's one of my favorite tests because it's a huge time saver. Again, we're looking at the compression of each cylinder. Now, again, they call it relative compression because we are inferring the compression of a cylinder based on the starter draw. But remember, that starter is pushing on each of the cylinders. Now, keep in mind, you have to have a healthy starter. You have to have a healthy battery. That's important as well in order for this to be an accurate test. But I think most of us can tell whether a starter is functioning properly or if the battery is fully charged or needs to be replaced. And, in some cases, we can hook up a jump pack if we just need to do this test and the battery's not good. And if the starter's not great, which you do encounter sometimes, there'll be some bad spots in the armature of the starter, and you get some dropouts. Well, maybe this test isn't going to work, but 90% of the time, it is a quick, easy test. Now, here's my opinion on relative compression tests. And this has been said before in training that I've gone to, and I think it's very true. A lot of techs go this route, and I still see this when I go into shops and I come in for a diagnostic, that technicians will go through, let's say they have a misfire on a cylinder, right? They're trying to diagnose a misfire. Why isn't cylinder 1 hitting? And they'll check spark. That's traditionally one of the easier checks that we can make. And then they'll check fuel. Okay, that's the next check they make. And then after those checks, then they check compression, because traditionally that was a little bit more work. We got to get the gauge out, we got to hook it up. And I feel like now with a relative compression test, this should be your first check. I think on any misfire diagnosis, and I've added this to my, my testing process. Any misfire diagnosis, and heck, even any drivability concern where the engine isn't running right, you should do a relative compression test first. Maybe not before you do anything else. You can pull codes and look at the data and stuff like that, but it should be one of your first tests to analyze an engine. Let's make sure that the mechanical state of this engine is correct before we proceed with anything else, because there's no point in chasing fuel trims or looking at spark or fuel if we've got a low compression cylinder or something that doesn't look right on our relative compression test. Is such a powerful tool. Now, going back to how to do this test, I said we're going to do this with an amp clamp. That's my preferred way. Do keep in mind you can actually do this just by battery voltage. If we utilize Ohm's law, you realize that the amperage and the voltage are going to have a relationship. Okay, so as the amperage draw goes up, as that starter's fighting against a compression stroke, the voltage is going to drop. So it's going to be inverted if you were to look at it on a scope, but you can actually get a relative compression waveform based off of the battery voltage using the scope. I don't use this method very often, not saying there's anything wrong with it, but let's say you bought a scope, and every scope's going to come with some type of voltage lead. If you don't have the amp clamp, there's still a way you can do this. So I mean, even with a basic U-scope, you can still do this. So when we're doing this test, just a couple more things that I'd like you to know. Number one is you are looking for something that is different than the rest. Now, generally, this is going to be a peak that is lower than the rest. Because if you were to look at a relative compression waveform, if you've never seen one before, and you're looking at that line on the scope, it's going to be like a succession of mountain peaks. Okay, you're going to see it go up and down and up and down and up and down, and they'll kind of look triangular as it represents each cylinder. And you want all those peaks of the mountains to be even. That's ideal for most engines. Now, keep in mind that if it's a high mileage engine, there's going to be some variation. There's going to be some cylinders that are worn down a little bit more than others, but we can use this with our other symptoms. And I think that's true for any of these tests. We don't want to just rely on one. Let's use it with our other symptoms. So if we have a P0301, cylinder 1 misfire, and we do a relative compression test, and we see that cylinder 1 has low compression on our relative compression test, okay, well, now we know we have a good direction here, because we've correlated, okay, there is a misfire on this cylinder. I saw it in the codes, I saw it in the misfire counters, and I saw it on the relative compression. You know, that second test validates the direction that we're going. It's always important with any of these tests. And it's something too, you know, as you start using new tests, something that you have not used before, I think it's important to use your familiar tests that you know that you can rely on, and you know the results. You know exactly what to expect. Use them in correlation with a new test. So let's say you do a relative compression test for the first time and you get a result that, yes, this cylinder is low. Confirm it with a traditional compression gauge. Now, this will be time consuming at first, but it is going to allow you to really understand the test that you're doing to validate that, yes, this is correct. What I am seeing is definitely correct by using testing methods that we already know. Heck, you can do this on a vehicle that's broken. Okay, let's say you already know that that piston has a hole in it. All right, let's do a relative compression test on it and see how it looks. I think that's a really, really good thing to do. You can use these tests on a known bad, and it's going to show you what you would expect to see if there's a problem. The opposite is true as well. You could do this on a known good. I think any test that we do, you know, we're looking for an expected result. You shouldn't be doing a diagnostic test if you don't expect a certain result. Now, you don't know what you're going to get, and that's the point of doing the test, is we want to see, what do we actually get from that measurement, but there should be an expected result. For example, if I take a voltmeter and I put it onto the positive and the negative terminals of a battery, I expect to see 12.6 volts if it's fully charged. But let's say I get 5 volts. Okay, there's my problem. And that's a simple example, but for any test, especially something new that we're not familiar with, we want an expected result. And the only way to have that knowledge is because, I've tested a battery before. I've been trained to know that 12.6 volts is a fully charged battery. Same thing's true with the relative compression test or any of the scope tests that we're going to talk about, is we need an expected result. And a great way to do that, again, is to do these tests on a known good vehicle, on an engine that you know has no mechanical problems. This thing's running top notch. Maybe it's brand new. All right, let's see what that waveform looks like. Really, really important. That applies to really any testing method or tool that we're using for the first time. Let's play around with this and let's see. And again, going back, we can use a known bad. When you know you have a problem, you've diagnosed it using your more familiar methods, we'll add this one in at the end just to see what it looks like. So next time, if you see that, okay, I saw that last time, that's going to be my issue. Let's talk about some stuff that we want to watch out for as we're doing relative compression tests. And these are just things that you don't want to get hung up on. All right, number one, there is a video actually. Super Mario Diagnostics has this. I'll put a link to it in the show notes. If you have washed cylinders, which means that so much fuel has entered the cylinder, it is going to actually reduce the compression of that cylinder because we need that oil on the cylinder walls and on the rings for it to seal properly and create compression. And once that cylinder gets washed, it's going to drop in compression significantly, and you're going to get a low number. Now, this would show up the same way on a gauge, but I do just want everybody to be careful. Just because you see a cylinder that is low compression doesn't always mean there is a mechanical fault. Now, the way to prove this out, or at least the way I do it, you can add a small amount of oil into said cylinder and see if the compression increases. And if it does increase, we know, a significant amount, we know that we have a washed cylinder wall. And then the next step would be, okay, why do I have a washed cylinder wall? Is it an injector problem? Do I not have spark on the cylinder? So on and so forth. Not really the point of this, but just something to watch out for. Just because you get a low peak or what reads on the scope as low compression doesn't always mean that there's definitely a mechanical problem with that engine. Now, yes, technically that's mechanical because it's not making compression, but there's no failed mechanical component. Another thing you want to watch out for when you're doing a relative compression test, keep in mind if you're doing a relative compression test on an inline engine, 4 cylinders probably the most common that most of us are going to run into. Okay, so all 4 cylinders are in line with each other. And let's say there is a timing issue on this engine. Okay, the valve timing is incorrect, and you got some misfires going on. It's running pretty rough, and maybe you have a code, maybe you don't. Well, but let's say the valve timing is off. That will cause low compression on that engine in most cases. And if the timing's off on an inline engine, that's why I'm saying it's inline engine, the compression will drop, but it's going to drop evenly for all the cylinders. So if you just take a quick glance at your relative compression test, you'll say, oh, they're all even. Now, all even doesn't necessarily mean good. We can actually look at the amperage difference from peak to valley of this waveform. And for a normal gasoline engine, again, where the battery's in good shape and the starter is in good shape and there's adequate compression, we want to see somewhere in the neighborhood of, I would say, 50 to 80. And again, that's from peak to valley. All right. So the total average amperage, it depends on the engine. You're going to see it somewhere, 150 to 200 amps, somewhere in there, cranking amperage. But what I'm talking about is if you look at the valley, That's the lowest point, and you go to the peak of the mountain, if you were, the compression stroke, and you look at the difference. I see 60 amps a lot of the time. So what I'm saying by this is you can actually infer that all cylinders are low based on that amount of amperage. Now, this can get tricky because what's a good number for a particular engine? Again, that's when having some known goods and doing some testing can really help you, but it's just something to watch for. You can actually identify that an entire engine is low on compression because of a timing issue. Now, let's say we have a V-style engine and it has two different chains or a setup where you could have one bank go out of time but the other bank is in time. You'll actually see alternating peaks. You'll see one go high and then the next one go low and the next one go high and the next one go low. That's generally the firing order for V6, V8 engines. That's a little bit easier to identify a timing issue that way. But in an inline engine, not always so easy. So just keep that in mind. Look at the peak to valley difference in amperage. And again, somewhere around 60 is my number. I know that's probably not perfect, but it's generally where I look for those numbers to be to represent proper compression. Now, there are some other correlations that you can do. I've heard that you can actually go just 1 amp of current draw to compression, and it'll be pretty close to the compression of the cylinder. I can't say that's always true, but take a look and see what you come up with there, see if the numbers match up. Another thing we see in these relative compression waveforms is we see very commonly when we have a low cylinder, okay, a low compression cylinder, the following cylinder in the firing order is going to be higher, much higher. So let's say we come up on cylinder 1. Cylinder 1 has low compression, and so we have a very low peak. Okay, this mountain peak is much lower than the rest of them. After that low peak, the next peak is much, much higher, significantly higher. Now, we don't see this in every single engine, but we see this a lot. Don't get thrown off by this, because you'll see one cylinder that is really high, and it maybe masks that other one that's next to it that's low, and you're like, well, what's up with that one? That one's extremely high. It's really the one that is low. Now, there's been some discussion on why exactly this happens, and to be totally honest, I don't really feel comfortable explaining it myself because I don't totally understand it. But if you go searching through some Facebook groups, there is some great discussion on exactly why this happens. And again, it doesn't happen in every case, but it's something that you might see. And I'll say it's normal to see that, to see the next cylinder be significantly higher than the rest. Now, there's always variables. I'm going to throw some more variables at you here. If you have a cylinder that has a stuck closed exhaust valve, okay, and that happens for a number of reasons, this will actually also cause a high cylinder peak. Let's take a 4-cylinder just to make this easy, and let's just say, again, to make this easy, that the firing order is 1, 2, 3, 4, all right? So let's say cylinder number 1 has a stuck closed exhaust valve. All right, that means when the the piston comes up in the cylinder on the exhaust stroke, the exhaust valve does not open and we cannot evacuate that spent exhaust gas, or if it was just cranking the air, but we can't push it out. All right, and so this would cause a misfire. And during a relative compression test, what you're going to see here is not a low peak. You'll actually see a peak that is about twice as high as the rest. Now, here's the reason why. Think about how an engine works. Let's find our partner cylinder here. We need to find our partner cylinder. So 1, 2, 3, 4 is our firing order. To find a partner cylinder, you split the firing order in half. So it'd be 1 and 2, and then 3 and 4. Stack them on top of each other. Okay, so 1 and 2 would be on top, 3 and 4 would be on bottom. The numbers that line up, those are your partner cylinders. So in this case, 1 and 3 are my partner cylinders, meaning that those pistons are in the same position, okay, whether it be top dead center or bottom dead center, but on opposite strokes. So that means when cylinder number 1 is coming up on its compression stroke, cylinder number 3 is coming up on its exhaust. And the opposite is true as well. When 3 is coming up on its compression stroke, 1 is coming up on its exhaust. So let's go back to our imaginary problem. Cylinder number 1 has a stuck closed exhaust valve. When cylinder number 3 is coming up on its compression stroke, we're loading the starter, right? Well, cylinder number 1 is supposed to just be pushing some air out through an exhaust valve. Well, it's not doing that right now because the exhaust valve is not open. And since the intake valve is closed during the exhaust valve, guess what? We've got a second compression stroke happening here. So what's going to happen is on number 3's compression stroke, you'll actually see what will look like a double in amperage peak. This will be twice as high as all the rest of the cylinders. And this is what we see when we see a stuck closed exhaust valve. So another thing you got to watch for. Again, lots of variables, and this is why we've got to practice with these testing methods so that we can identify some of these issues. But again, if you're well versed in using this test, you can pick that out pretty quickly. And you can actually probably hear this as well. And that's one of the things that I did want to bring up as well, is that don't forget about your ears. I say we should always do a relative compression test. Well, honestly, what I do before I even take out my scope is I will see if I can do a clear flood, which on a lot of vehicles you can. Again, that's holding the accelerator all the way down to the floor, cranking the engine over. It should disable the fuel injectors. Again, it's not every vehicle, but on one that has it, I just do that. If I got a misfire, that is immediately what I'm doing. I see a P0301, okay, clear flood, crank this thing. Listen to it with your ears. All right, you can actually hear a cylinder with low compression, or heck, cylinder, in that situation where it's the double loading the starter or the stuck closed exhaust valve. Technically, you don't have low compression on any of those cylinders, but it's not rhythmic. The starter and the engine should sound very smooth, very repetitive. There shouldn't be a stop or a bump in that starter. It shouldn't speed up and slow down at any point. Now, again, you know the noise of a starter. Everyone's heard one. It's going to go rah, 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 rah. But it should be very rhythmic in that noise. It shouldn't go rah, 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 rah. That's the starter speeding up, or it could even be slowing down at a certain point, and that is indicating to me, hey, I got a mechanical problem. So let's say you didn't want to buy any of this stuff. Heck, you can use your ears and pick out a compression problem very, very quickly. I really try to stress this with my students to help them find mechanical problems before they take almost any diagnostic step. Now, the advantage to the relative compression test is going to confirm to us, and it's also going to allow us to tell which cylinder. You can't do that with your ears. Now, I haven't mentioned how we do that, though. How do we know? We're looking at these peaks on the waveform. How do we know which one belongs to which cylinder? We're going to bring in Spark to help us. Now, you're going to need a second channel on your scope, and that's where maybe like a U-scope, you wouldn't be able to necessarily do this, but we're going to sync. Heck, you could sync to any cylinder. I like to do number 1 because all the firing orders start with number 1, but we're going to sync to that cylinder spark. Now, you can do this with whatever lead you want. You can use an inductive lead of any different kind. It's going to depend on the setup that you have. If it's using a coil over plug or plug wires, whatever the setup is. But really what we're doing, we're getting a second channel up while we're doing this relative compression test, and we are looking at where this spark happens. Now, the spark for number 1, our spark event happens at top dead center of our compression stroke, or very, very close to it, just before top dead center on our compression stroke. And we know that we can rely on that. And so wherever that spark line lines up with, that peak is our number 1 cylinder. And from there, we pause the waveform and we just count to the right using our firing order. So if the firing order is 1, 2, 3, 4, okay, we found cylinder 1. There's 2, there's 3, there's 4, and then we see 1 again. And that way we can identify which cylinder is, which cylinder has low compression. That's what we're looking for. Or which cylinder is different than the rest. And so that way, again, this is why it's such a huge time saver, because we could identify on a V8 engine which cylinder has low compression. Now, maybe you have a misfire code to help you with this. And again, I definitely recommend, let's get, as I think Jim Morton would say, let's get 3 arrows in that target to make sure. If we get a misfire code for a P0302 and our relative compression test shows us that cylinder 2 is low, based on that sync, that spark sync, we really know where we're going. And we can take some other steps to figure out exactly what the problem is. But being able to identify which cylinder without taking anything apart, that we got low compression on this cylinder within a matter of minutes, it's just such an awesome test to have. Now, if you did have a scope with only one channel, there is another possible way to identify which cylinder is low compression. You could remove a spark plug from a cylinder that you know which cylinder it is. Okay, so for example, let's say I do my relative compression waveform with my U-scope, which only has one channel. I can't add a sync. We could look at the engine and we could say that is cylinder number 1. Okay, I'm going to pull cylinder number 1 plug and I'm going to redo that test. And you can compare it to your first test and you could say, okay, there's cylinder number 1. I know that cylinder number 1, that there's 0 compression on there because I took the plug out. And now I can count over from that spot. Now, maybe you guessed right, and cylinder 1 was the low compression. That can get tricky. It's not the most reliable method because if you have 2 cylinders with low compression, especially on a 4-cylinder, it's going to be a real messy waveform. But it is possible that you could do that if you did not have a second channel to sync to spark to identify which cylinder is which. But again, we can also use our stuff like misfire counters and misfire codes to help us do a traditional power balance test. Again, this will still lead you in the direction of, yes, I got low compression on this cylinder. Going back to using a particular sync, and we talked about spark. The reason that we use spark to sync to, okay, so if I'm syncing to number 1, I'm going to read the spark off of number 1 cylinders because we know when spark happens. It's going to be around that top dead center of that cylinder. Depending on the application, that can vary a little bit, maybe a little bit advanced, maybe a little bit retarded even in a scenario where there's some sort of catalyst heating strategy, stuff like that. But it's going to be around that top dead center of that cylinder, and that is always going to be the case. That spark's not going to really move too far from that point in time. Some people I've seen have tried to use fuel injection as their sync to a cylinder. We can't use this. And the reason being is we don't know when that injection event is going to happen for a given cylinder. I've seen injection events happen almost anywhere within the 4-stroke cycle, depending on the application, and it's just too unreliable. So my point of this is don't use fuel for a sync. If you're going to do a relative compression test, use the spark. That's going to be your best method there. So I'm going to give you part of a case study here. We're actually going to make this into a 3-part series because as I got talking about this relative compression test, I realized how long I've been talking about it, and this is going to be a very long podcast if I talk about all 3 of the different scope methods that I want to talk about. So we'll get this out in a 3-part series. But I had a vehicle this week. It was a 2007 Chevrolet Suburban, and I used a relative compression test on this vehicle. Here's what the shop said when they called me. So we just, now the background, this is an engine that has active fuel management, which means on cylinders 1, 7, 4, and 6, I believe, number 1 for sure, they have lifters that can collapse and stop valve movement. And when you're going down the highway, they switch from a V8 to a V4, saves on fuel economy, okay? These trucks had a ton of problems with these systems. And 2007, we're seeing a ton of these vehicles in the shop right now, and I'm sure many of you have as well. And so they had an issue with those components. And I don't know exactly what it was, but I'm not surprised to hear that. So what they did was they pulled the heads off. They replaced the VLOM, we call it. This is the solenoid assembly that sits in the valley of the engine between the 2 cylinder heads, controls oil flow to lifters that shut down valve operation. They also replaced all the lifters, and this is all 8 cylinders lifters, including the active fuel management ones, which are different than the cylinders that don't shut down. So they replaced all that, obviously all the other gaskets and stuff that went along with it, and they said afterwards they had a misfire on cylinder number 1. And they swapped the injector, swapped the coil, pretty typical stuff, and they even checked compression on cylinder number 1. And it read proper compression on their gauge. 170-ish psi. That's good for that engine. So what's the issue here? Why are we having a misfire? And that's why they called me in. I was able to identify what was going on. Not exactly. And actually, I used another test to confirm this, which we'll talk about in the subsequent episode. But my first test was a relative compression test. Okay, I did actually look at the scan tool. I looked, okay, it is misfiring on cylinder 1 consistently when I start this thing. I did my cranking test with my ear, and I heard something that wasn't quite right. I heard that starter change pace every 8 cylinders, and okay, I know where I need to go. So again, relative compression test. Let's hook up. Let's sync. It is on number 1, and we actually see this number 1 cylinder dropping out. Okay, that's great. That's easy. No compression on cylinder 1. Why did their gauge show compression though? And this is where some of these scope tests can really come into handy. And we're going to talk about a couple different tools as well, a couple different testing methods as well in subsequent episodes that we can use in conjunction with our relative compression test. But if you watch the relative compression test, if you were to look at the engine from the time I hit the key until the time I let go, and it cranks the whole time, 5 to 10 seconds, we can watch all the compression peaks. Now, from the start, I actually see about 2 engine revolutions where all 8 cylinders are hitting. They all have even peaks. I was like, oh, okay, that's interesting. We have compression on all of these cylinders, and then it drops off. Then all of a sudden, we don't have any compression on cylinder number 1. So what happened during that point? And I'm actually going to leave it right there because I used some other testing methods to figure out exactly what was going on. And maybe if you've worked on these engines, you already know what's going on. But that's why their gauge showed compression. And that's where some of these scope tests can really shine, because they hooked up their gauge, and those first 2 engine revolutions showed compression on the gauge. And that's the gauge with the Schrader valve in the hose is going to stay. That needle is going to stay right there. It's going to show you, yep, you got 170 psi. And my relative compression test showed me 170. Oh, there goes it. Nothing. My ears told me that too, but the relative compression test confirmed it for me. That the first 2 revolutions, that cylinder was capable of building compression. After that, there was nothing. And while it was running, that was the same case. And I will continue how I diagnosis that one in the next episode using some of these other scope methods. One other thing that I did forget to mention, and I wanted to bring this up, if you work on Fords and you have the IDS, don't forget there is a built-in relative compression tool in the scan tool. You don't even have to have a scope. And I've actually used this test with Autel and Launch as well. They stole that software from Ford, and it works great. And what it's actually doing on these Fords, it's not on every single one of them, but a lot of the newer vehicles, it does have this, is it's watching crank speed. It has you crank the engine for 10 seconds. So you do need a strong battery for this one, because 10 seconds of cranking does wear on the battery a little bit. And if the battery is not at full health, this is going to affect the test. But you're doing this through the scan tool. You're going to relative compression test under the special functions in the powertrain control module. It gives you the instructions. You crank it. It breaks it down for cylinder, and it gives it to you in percentages. And the IDS will do this, factory Ford scan tool. My Launch will do this. My Autel will do this. Really, really handy. So if you work on Fords, guess what? You don't even need a scope for these tests. So we have 3 different ways we can do this. We can do it with our ears, we do it with a scope, and some of them we can even do it with a scan tool. Anyways, that's relative compression. Thank you for listening, and make sure that you check out the next 2 episodes that I'm going to try to get out as soon as possible, where we are going to talk about pulse sensors. I've talked about the people that make these, but let's really talk about using them. And one of my favorites, just because I'm a nerd about this sort of stuff, in cylinder pressure testing. I actually find some of these other tests to be more practical and useful, but I really love in-cylinder pressure testing. It is so cool to see what's going on inside a cylinder. So make sure to check those out. And hey, if you're enjoying the podcast, if you do me a favor, go on to whichever podcast service you're using and give the show a rating and or review. I would really appreciate it. I appreciate you listening. Everybody have a great day. Let's get out there, start fixing the world one car at a time.